Alright, welcome back, EHS 300. And in this particular video, we're going to focus on drinking water disinfection. And we're going to put a greater emphasis on chlorine disinfection because at this point in U.S. history, chlorine disinfection still is by and large probably the most common disinfection strategy being employed. So on the cover here, I've got some images, one just showing you ultraviolet treatment methods that exist and how 254 nanometers of light using UV light bulbs that are at that range are the most capable for disinfecting. Also here, you got a truck delivering chlorine, and then chlorine can also be delivered in 55-gallon drums. Previously, we discussed some of the different purification steps, particularly related to doing coagulation and flocculation. Then there was sedimentation, and then the water that comes off the top of the sediment basins is then filtered, and then ultimately after it's filtered, we can then do disinfection or any additional treatment processes. So it's good to remember that we don't want to just put water right into direct contact with a lot of chlorine right from the get-go, because a lot of the chlorine is going to interact with the sediment and all the other dirt or whatever might have been in that water. So when that chlorine interacts with that organic matter, which could include humic acids from the soil, tannic acids from leaves or nuts that have fell into the water, so all of that in the water, when it interacts with chlorine, produces disinfection byproducts, which we know are also carcinogenic and they're regulated. So water plants don't want a lot of that. So they may add a little bit of chlorine at the beginning, but not much, and its purpose is not for disinfection. So generally, a lot of plants don't add chlorine until way back here. That was not always the case. They used to add chlorine right up front, a lot of it, but the disinfection byproduct rule in 1997 put a stop to a lot of excessive chlorination, and that has reduced cost. You don't need as much chlorine if you use it on clear water rather than using it on muddy water up front and then using it again. So we know these steps from before, so we've went through these already. I'm going to move on in the slideshow to the steps that pertain to disinfection now. So we're at the point where we've done all of these. So we're at disinfection. So disinfection is the removal of the infectious capability of the water, or the infectious capability of the surface or the food or whatever. So it is the destruction or inactivation of pathogens, things that could potentially make us sick. Pathogens are disease-causing agents, so disinfection is destroying them. Disinfection is not necessarily the total removal of all life. Now that may happen and when you're using strong disinfectants, but we're not removing all life. We're removing the infectious agents. And generally, in water supplies, infectious agents that thrive, particularly in the fecal oral parts of our body, so they get transmitted through the fecal oral route. They do well when they come into our mouth, but they do really well when they get into our GI tract and our stomach. Those things have a preference for those areas. They don't tolerate the natural environment as well as they tolerate being inside their preferred host. So the addition of some of these things have allowed us to improve the life expectancies of a number of people around the world. So what we can potentially do with our clear water at the end is we can hit it with chlorine gas. We can hit it with bleach, sodium hypochlorite, which is also chlorine. Ozonation is something that's been considered, and it's used quite commonly in Europe and Canada, as well as in Milwaukee, Wisconsin, as you saw. Ultraviolet light, using UV light on very clear water, can also destroy the DNA and the RNA of potential pathogens. And we could also combine these methods. So disinfection, it's important to realize that we're disinfecting the water, which is different than sterilization. Sterilization may involve like an autoclave, or there's gases like ethylene oxide. that can kill everything, all life. It's not feasible to take all of our water and autoclave it or to hit it all with ethylene oxide. It's more affordable, and all we need to do is disinfect. So disinfection is our goal, not sterilization. We'll skip that. So chlorination. When chlorination is done, whether you're using chlorine gas, whether you're using bleach, which is sodium hypochlorite, the chlorine dissolves in water and forms two disinfecting agents. One of them is more potent than the other. So these two disinfecting agents when chlorine interacts with water. So first, let's back up. What's the molecule for water? H2O. So two hydrogens and an oxygen. And the way they're held together, you guys kind of seen the Mickey Mouse looking picture, the two hydrogens around the oxygen. So H2O. So when H2O interacts with chlorine, it will form HOCl. So we lose one of the hydrogens and chlorine is now bound. Or we've potentially got no hydrogen here at all, and we've got what are called hypochlorite ions. In the abundance of a lot of hydrogen, so if we have a lot of hydrogen in our water, we have a pH that's more acidic, it's more acid-like. We will form more hydrochlorous acid or hypochlorous acid. So when you think of the acids, remember from our pH conversations in the last section? Hydrochloric acid, its formula is HCl. Hydrofluoric acid, HF. Nitric acid, HNO3. So acids in general have hydrogen in them, a lot of hydrogens. So water that has a lot of hydrogens in it is more acidic. So when we add chlorine to water that has a lower pH, it favors the production of more acid, and it favors production of more hypochlorous acid. So lower pH waters are more dangerous to the pathogens, which is good for us when bleach is present or chlorine is present. Higher pH waters, when the higher pH and we have more hydroxyl groups in the water, more O's, more free hydroxyls in the water, we will form more hypochlorite ions. Hypochlorite ions can also kill pathogens or deactivate them or whatever you want to call it. So we'll still form these, we'll form an equal amount at a pH of 7.0. As we become more acidic, we'll form more of these than these. And as we come totally, like if we had a pH of like 0, this would be all we're getting. But usually water is in between a range of 6.5 to 8.5, so we get a lot of these. And those really just affect your chlorine demand. They affect your amount of chlorine you need to use. So what is chlorine demand? So chlorine demand is this amount of chlorine that is needed to not only oxidize all the dissolved organic and inorganic substances in the water, I mean that's a big part of it, but chlorine demand is the amount of chlorine needed to pretty much, I'd say, interact with everything that's in the water. So it's the same thing, but there's stuff in the water that we know is like organic and inorganic that will bind or interact with the chlorine. So chlorine demand is how much do you need just to deal with all of the organic and inorganic substances in the water. So the chlorine will interact with stuff that's in that water early on. We know that chlorine indiscriminately reacts with substances in the water. These aren't like antibodies where chlorine goes out and seeks out or looks for certain things and attaches to certain things. Chlorine is a very reactive compound. So we're interested in having a residual chlorine at the end. So we'll add a lot of chlorine, and if all the chlorine we add is used up, then we haven't quenched or met the chlorine demand. Which water do you think would need more chlorine added to it that have some left over that's unbound. If we added a bunch of chlorine to this, a bunch of chlorine to this, which one would have the most chlorine left over as free chlorine? Chlorine, part of our chlorine residual. Hopefully you think this one would have the most left over that's unbound. A lot of our chlorine would be bound here and form also a lot of reactive oxidative species. It would form a lot of disinfection byproducts. So we wouldn't want to chlorinate this water. We would want to clear this water up first. So again, chlorine interacts indiscriminately with substances in the water. One of the first things that's formed, and some people even make the they run their water plants using these as their type of chlorine. They use chloramines, but chloramines are also formed naturally when we add water, and that water has organic matter in it, to chlorine, or when chlorine is added to water with a lot of like ammonia and a lot of organic matter, will form these. So chlorination, requires us to add a lot, and the amount that we might have to add is dependent upon how much is in there in terms of both non-living and the microbes. So we may not necessarily need to use a lot, but if we've got a lot of non-living substances in the water, we would need more chlorine to prevent the microbes from escaping disinfection. So there's an approach that's used to prevent the escape of microbes from disinfection, and the approach is called breakpoint chlorination. And breakpoint chlorination is used to ensure a sufficient amount of chlorine is there to disinfect and maintain adequate disinfection throughout the entire distribution system. So there's this figure here that shows you a graph. And over here on the left, this is the amount of available chlorine that's able to still treat and disinfect. This is the amount of chlorine that we've added. So from here to here, we've added chlorine. And yet, none of it is available to disinfect. None of it is residual. It's all used up. They don't put numbers on this figure because it's dependent upon the quality of your water. If you have crystal clear water with nothing in it, as soon as you add chlorine, you might just immediately go up without having a breakpoint at all. But we don't have crystal clear water. Natural water has stuff in it. Even after we've done coagulation, flocculation, sedimentation, filtration, we've still got water that has stuff in it that will react with the chlorine. So water plants don't do this every day, but they know what these are like for different times and seasons of their year. So in this example here, notice that as we add chlorine, the first bit of it is immediately destroyed by reducing compounds. So there may be things that are in the water like free iron. There may be things in the water like nitrates, ammonia, humic acids. They will start to react with the chlorine, and as they use them all up, there's no residual. But we keep adding a higher concentration of chlorine to that same water, and as more and more chlorines added, we start to form chlororganics and chloramines. These are short-lived compounds that will also continue to react with other things. So as we continue to add them, we will see an increase in concentration in the amount of residual. So this is actually able to kill things. It can disinfect. This is able to disinfect. However, the amount that we add, as we continue to add it, and even if we don't continue to add it, these levels will fall quickly. So as we continue to add it, and then also over time, we will be destroying, and then over time we will see a destruction of the chloramines. And we will hit a place called the breakpoint. And at a certain point where you've added enough chlorine to overcome the formation and destruction of all the chloramines, you've quenched all the reducing compounds, you will be at this point where you have free available residual chlorine. So everything added from here on is available to disinfect. They call this the breakpoint. So let's review that. Step 1, chlorine is added and is immediately and quickly reduced by readily oxidized matter, like metals, like iron and manganese, hydrogen sulfide gas, NOM, which is called natural organic matter, ammonia. All the chlorine is used. There's no free chlorine, there's no chlorine residual. Chlorine residual includes free chlorine, just Cl, or hydrochlorous acid and hypochlorite ions, right? And it also includes chloramines. So chlorine residual includes chloramines. Free chlorine is not bound to ammonia. It's just the hypochlorous acid and the hypochlorite ions. All right, so breakpoint chlorination, step 1. We add the chlorine, it's all bound. And they're not just bound, it rapidly reacts, and no free chlorine and no chlorine residual is left. Step 2, as more chlorine is added to satisfy the demand, particularly with respect to the ammonia in the water and some natural organic matter, we will form chloramines. Chloramines will increase with increasing chlorine dosage. But if the dosage stops over time, or even as you add more chlorine, you will stop favoring the production of chloramines. And again, chloramines are quickly degraded. So we see this decline in chloramines. Next, so step 2, we form the chloramines. Step 3, as more chlorine is added, the chloramine levels peak and fall, and they keep falling until a breakpoint is reached. So the chloramines and chlororganics are destroyed by adding more chlorine, and they're also destroyed by other things in the water. Step 4. Eventually, if we keep adding chlorine, we'll have actually caused the chlorine to interact with all these compounds, and we have destroyed them all, but we'll get to a point where it switches back over to this spot, the breakpoint. So upon adding more chlorine, the chloramines and chlororganics are completely destroyed, and now the addition of chlorine will not form chloramines, but will form free chlorine. So here, chloramines are included as a type of our residual. They can disinfect, but they're short-lived, and adding more chlorine destroys them. We want free chlorine, so we keep adding chlorine, and we get to this point. This is the point we want to be. Chloramine has a formula that looks like that. That's an amino group attached to, or an amine group attached to chlorine. Free chlorine is just the good old-fashioned chlorine dissolved in the water. So free chlorine is just our chlorine here, and then when it interacts with water, as the water's pH goes up or goes down, we form more or less of these hypochlorous acids and hypochlorite ions. And this is got, I would say HOCl plus HCl. That's our formula for what you get. That's all hypochlorous acid, but here HOCl is what we call hypochlorous acid, that's hydrochloric acid, but here Cl2 and H2O forms several of these. HOCl forms OCl in low pH water or in high pH waters. So hypochlorous acid is formed in acidic water. Hypochlorite ions are formed in basic high pH waters. Together, they are free chlorine. So, which one is better at disinfecting? Hypochlorous acid. Which one actually forms at lower pHs, at acidic pHs? Hypochlorous acid. Can OCl, hypochlorite ions, can they disinfect? And yes, they can disinfect. Together, they are called free chlorine. So we still form hypochlorite and hypochlorous acid groups or chemicals in water with pHs of like 6.5 to 8.5. We form both of them. It's just when it's acidic, you form more of the acid. When it's basic, you form more of the hypochlorite ions. All right, so when we do disinfection, there are a few different types of disinfectants out there. There's chlorine gas. There's hypochlorite solutions, like bleach, which we can buy in drums. Sodium being the most common one, but you can also order calcium hypochlorite. Concentrated sodium hypochlorite, it can be dangerous. I've had to lug those drums downstairs into a clear well, back in the day. When I worked for the state of Ohio, our 3C camp had a clear well that we treated the water that leaked through a big field, groundwater, and that stuff would need to be treated. We disinfect it, and lugging them drums up and down those steps was tough. And I was worried if the drum fell or spilled, how nasty that stuff could be if it touched you. The good thing is the smell of it, although it would be bad, isn't as crazy bad as the gas. It's still dangerous if you inhale it, especially in a confined space, but the gas is way dangerous. Richmond Utilities used to use chlorine gas. Chlorine gas is actually a bioweapon. It was formed by Fritz Haber back in Germany. He was a Jewish guy, and he actually got a Nobel Prize for figuring out how to take ammonia and form ammonia fertilizer because people were starving to death. And he figured instead of fighting wars over bat guano for ammonia, that what he would do instead is figure out how to get ammonia from the atmosphere. So he figured that out and made ammonia from the atmosphere. And something like half the nitrogen in our bodies to support the whole planet actually with our food and our agriculture through our fertilizer was through the Fritz Haber method. And you can Google and read up on Fritz Haber. He was a Jewish guy, so they used some stuff that got pretty bad against him and his people during the Nazis and during their kind of campaign. And one of the things that he did when he thought he was doing the right thing for Germany, when the rest of Europe was kind of treating Germany like they were, lesser, which kind of fueled some of the irritation within Germany and some of the conflict, he, along with his lab, thought they were doing the right thing by figuring out how to create chlorine gas. And then they used chlorine gas on the Allied forces and chlorine gas as a bioweapon. And you can read about this. It's kind of crazy history. And then his lab, a lot of his people left the country. He eventually got out. His wife and kids, his kid committed suicide. His wife and kid they were in the U.S. They were so ticked off at him for creating this gas and using it on the Allies, and he was proud of it. And then eventually, after he left Germany, I guess the Nazis then used the gas, and not just that gas, but other gases that he had made in the concentration camps. So the guy gets a Nobel Prize for fixing our world's food supply, and then a few years later creates this horrible biogas and this horrible bioweapon gas, which is chlorine gas, as well as some other ones. So kind of crazy. But chlorine gas is actually a very cheap way of disinfecting water. but at Richmond, Lonnie, our water plant manager, is afraid to use it. So the things that affect chlorine and its ability to disinfect. Obviously, we want cleaner water, which will affect the concentration of the chlorine residuals. We know that the pH matters. So lower pHs tend to favor better disinfection or less needed time. And contact time. We need a sufficient amount of chlorine residual to be maintained over a period of time to continue to disinfect and to kill everything in there. So other methods of disinfection. So there are other methods that are out there, and again, why could you imagine that they're gaining approval and being better used? Well, one, we know that cryptosporidium from the Milwaukee video is resistant to lower levels of chlorine. Another reason was, in 1997 and 1998, when EPA actually put their rule out in response to congressional action from the year before, EPA promulgated the disinfection byproduct rule. And they said that these disinfection byproducts, THMs, trihalomethanes, and haloacetic acids, HAAs, they are dangerous for people's health. Therefore, we need less of them in the water so we can have less cancer. Many water plants had a hard time meeting the disinfection byproduct rule, so some of them explored using chloramines. Chloramines are less likely to form disinfection byproducts, but may make the water more corrosive. And that presented a problem that we might cover more here in a minute. Also, ozone gas. Ozone gas is very corrosive as well, and ozone gas is very short-lived, so it doesn't stay out in the distribution system. And then UV light also can disinfect. So we can use ultraviolet light. They use this at the wastewater plants in a lot of places in the US. On the very end of it, the UV light kills the bacteria. So we'll discuss more on the problems associated with disinfection and do a review here in a few minutes. I'm going to stop this video and see where we go from there.